Did you know there's ice on the moon? It's not a vast shimmering polar cap like we have on Earth, but something more subtle, more precious. Hidden away in the permanent shadows of craters near the lunar poles, where the sun's rays have not touched for billions of years, are frozen deposits of water. This isn't just a scientific curiosity, it's a game changer. This discovery, confirmed by missions like NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1, is the single most important ingredient for our future on the moon. It's the whisper of potential in an otherwise silent, barren landscape. It tells us that the moon isn't just a dead rock. It's a repository of the very molecule that makes life, as we know it, possible. This simple fact, water on the moon, transforms our celestial neighbor from a place we merely visit to a place we can stay. It shifts the entire paradigm of space exploration. Before, astronauts had to bring every drop of water with them, a tremendously expensive and limiting factor. Now, we can envision living off the land, or more accurately, living off the crater. This frozen water is more than just something to drink. It can be split into its fundamental components, hydrogen and oxygen. Hydrogen is a powerful rocket fuel, and oxygen is, well, what we breathe. The presence of this resource answers the first, most fundamental question of off-world settlement. Can we find what we need to survive? The answer appears to be a resounding yes. It beckons us, challenging our ingenuity and our ambition. It's a cosmic invitation, written in the language of chemistry, asking us to come and build. This isn't science fiction anymore. We've been there before. In 1969, we took a giant leap for mankind. The Apollo program was a monumental achievement, a testament to human will and ingenuity, driven by the geopolitical currents of the Cold War. But after a handful of missions, we stopped going. The moon hung in our sky, a destination visited and then seemingly abandoned. So why go back now? The reasons today are deeper, more sustainable, and far more collaborative than the race that first took us there. This isn't about planting a flag and coming home. This is about building a future. This is about staying. The moon is our cosmic backyard. It's only a 3-day journey away, a mere stone's throw in the vastness of space. Setting up a permanent base there is like building a research outpost in Antarctica or a deep-sea laboratory. It's a place to learn how to live and work in an alien environment, but with the relative safety of having Earth just over the horizon. The lessons we learn on the moon are the essential practice runs for our eventual, more ambitious journeys to Mars and beyond. The moon is the ultimate training ground for becoming a multi-planetary species. Think about the science. The moon is a 4.5-billion-year-old museum of our solar system's history, perfectly preserved. With no atmosphere, no wind, and no rain to erode its surface, every crater and rock tells a story. We can study the history of asteroid impacts, learn about the formation of planets, and even search for clues about the origins of life itself. A lunar base would give us a stable platform for telescopes, offering views of the universe untroubled by Earth's shimmering, light-polluted atmosphere. Moreover, the return to the moon is about uniting humanity in a common goal. This time it's not a race between two superpowers but a global collaboration. We are going back with rovers that can drive for miles, habitats that can sustain life for months, and drills that can dig for water. Living on the moon presents a set of challenges unlike anything we face on Earth. Our planet coddles us. It wraps us in a thick, protective blanket of atmosphere that gives us air to breathe, shields us from harmful radiation, and moderates our climate. The moon offers no such comforts. It exists in a raw, unfiltered vacuum. The first and most obvious challenge is the lack of air. A human exposed to the lunar vacuum would lose consciousness in about 15 seconds. It's an environment that is fundamentally, existentially hostile to life as we know it. Our entire existence there must be contained within pressurized habitats and spacesuits. Then there's the radiation. Earth's magnetic field and atmosphere act as a cosmic shield, deflecting the constant stream of charged particles from the sun, known as the solar wind, and blocking high-energy cosmic rays from deep space. On the moon, there is no global magnetic field and no air. Astronauts and settlers would be exposed to levels of radiation far higher than what is safe, increasing their risk of cancer and other health problems. We can't just walk around outside. We will have to live and work under shielding, perhaps buried beneath several feet of lunar soil or regolith, to protect ourselves from this invisible, ever-present danger. The temperature swings are also extreme. With no atmosphere to trap and distribute heat, the lunar surface is a world of brutal contrasts. In direct sunlight, temperatures can soar to a blistering 127 degrees Celsius, but when the sun sets, for a night that lasts 2 long Earth weeks, the temperature plunges to a mind-numbing minus 173 degrees Celsius, or minus 280 degrees Fahrenheit. Any structure, machine, or spacesuit must be engineered to withstand these wild fluctuations without cracking, failing, or freezing solid. It's an engineering nightmare that demands entirely new materials and technologies. Finally, there's the dust. Lunar regolith is not like the soft sand on an earthly beach. It is the product of billions of years of meteorite impacts pulverizing rock into fine, sharp, and abrasive particles. It's like microscopic shards of glass. This dust gets everywhere. During the Apollo missions, it clogged equipment, abraded spacesuits, and caused irritation for the astronauts. For a long-term settlement, this poses a serious threat to machinery, airlocks, and human health. We must learn how to manage it, control it, and perhaps even use it to our advantage. The moon, in its stark beauty, is an unforgiving place. So, how do you breathe on a world with no air? The answer lies in a beautiful bit of cosmic recycling. We won't have to ship every lungful of oxygen from Earth. Instead, we can make our own. The key is in the lunar soil itself. The regolith is made up of about 45% oxygen by weight. It's not free-floating oxygen, it's chemically bonded with other elements like silicon, aluminum, and iron in the form of oxides. The challenge is prying those oxygen atoms loose. It's like trying to get flour back from a baked cake, but with the right recipe, or in this case the right chemical process, it's entirely possible. Scientists and engineers are developing several methods to do this. One promising technique is called molten oxide electrolysis. You start by heating the lunar regolith to about 1,600 degrees Celsius until it melts into a molten lava. Then, you pass an electric current through it. Just like electrolysis splits water into hydrogen and oxygen, this process splits the molten oxides. Oxygen bubbles up at one electrode, ready to be collected and stored. This process doesn't just give us breathable air, it also gives us raw metals for construction. It's a 2-for-1 deal, provided by the moon itself. Of course, once we have the oxygen, we need to manage it carefully within a closed-loop system. The habitats for our lunar city will be like intricate self-sustaining terrariums. Every breath we exhale releases carbon dioxide. Advanced life support systems like those used on the International Space Station but on a much larger scale will capture that CO2. Algae bioreactors or chemical scrubbers will then break it back down, releasing the oxygen atom for us to breathe again. It's a continuous cycle, a man-made imitation of the great planetary cycles that sustain life on Earth. Nothing will be wasted. This concept of in-situ resource utilization is the cornerstone of a sustainable lunar settlement. The discovery of water ice at the poles adds another, even easier source of oxygen. We can simply melt the ice and run an electric current through the water to produce breathable oxygen and hydrogen for fuel. The ability to generate our own air from lunar soil and ice is what makes the idea of a city more than just a fantasy. It's the first step in transforming a hostile environment into a human one breath at a time. Where will the first lunar citizens live? Not in towering skyscrapers, but probably underground, or in structures built from the very ground they stand on. The need for protection from radiation and those extreme temperatures means we have to be pretty clever with our construction. The simplest solution is to go down. We could use natural lava tubes, these vast, underground caverns formed by ancient volcanic flows, as ready-made shelters. These subterranean tunnels offer built-in protection from the harsh surface environment. We would just need to seal them and pressurize them to create vast, city-sized habitats safe from the cosmos. For structures on the surface, we won't be shipping bricks and mortar from Earth. The cost would be, honestly, astronomical. Instead, we'll turn to the most abundant building material available, the lunar regolith. The same fine, problematic dust can actually be transformed into a construction resource. One of the most exciting technologies being developed is 3D printing. Imagine robotic rovers scooping up lunar soil, melting it with a concentrated beam of solar energy or microwaves, and printing out structures layer by layer. We could print landing pads, roads, radiation shields, and even the interlocking bricks for our habitats. The European Space Agency has already demonstrated this concept on Earth, using simulated moon dust to 3D print a 1.5-ton building block. The process, known as sintering, fuses the dust particles together into a solid, ceramic-like material. We could build domes and vaults, shapes that are naturally strong and efficient at handling the pressure difference between a breathable interior and the vacuum outside. These structures would then be covered with a thick layer of raw regolith, providing the necessary shielding from radiation. Our lunar homes will literally be made of the moon. The first habitats might be inflatable modules brought from Earth, which would serve as the inner pressurized bladder. These modules can be packed tightly for launch and then expand to create a large living space. The 3D printing robots would then build a protective shell around these inflatable structures. This hybrid approach combines the reliability of Earth-made technology with the efficiency of using local resources. It's a practical, step-by-step plan for raising a city from the dust of another world. A city needs power. On Earth, we are accustomed to a constant supply of energy, but the moon presents a unique electrical challenge. A day that lasts for 14 Earth days, followed by a night of equal length. During the long lunar day, solar power is an obvious and abundant choice. Vast arrays of solar panels could be unfurled across the lunar landscape, soaking up unfiltered sunlight and generating more than enough electricity to power habitats, rovers, and industrial processes. The lack of an atmosphere and clouds means solar power on the moon is incredibly efficient and reliable, but only for half the time. The real problem is surviving the 2-week-long night. The temperatures drop catastrophically, and solar panels go dark. A lunar city cannot simply shut down for half a month. Life support systems, heaters, and critical experiments must keep running. Therefore, a robust energy storage solution is non-negotiable. We would need massive batteries or regenerative fuel cells capable of storing enough energy from the 14-day solar bonanza to last through the 14-day famine. These would be far larger and more advanced than any battery systems commonly used on Earth today. These represent a significant engineering hurdle. One promising location for a first base is at the lunar poles, such as near the Shackleton crater. Here the sun is always low on the horizon, circling around like a midnight sun in Earth's Arctic. By placing solar panels on the high rims of these craters, they could receive near-continuous sunlight, dramatically reducing the need for massive energy storage. Some peaks may be in sunlight for over 80% of the lunar year. These peaks of eternal light are prime real estate for a solar-powered lunar settlement, providing a steady stream of energy to overcome the long, cold night. For a larger, more power-hungry city or for bases located away from the poles, we may need nuclear power. Small, compact nuclear fission reactors like the Power project developed by NASA are designed to be safe, reliable, and capable of providing steady electricity for years, regardless of whether the sun is shining. Powering our lunar dream will require a combination of solar ingenuity and nuclear reliability. Humans cannot live on recycled air and stored rations alone. For a truly sustainable city on the moon, we need to grow our own food. The psychological benefit of seeing green, living plants in a sterile environment would be immense, a taste of home 250,000 miles away. But lunar agriculture is a formidable challenge. The lunar regolith is not fertile soil. It lacks the organic compounds and microorganisms that plants need to thrive. It also contains heavy metals that could be toxic. We can't just plant potatoes in the moon dust and hope for the best. The solution will be advanced hydroponics or aeroponics, taking place inside pressurized, artificially lit greenhouses. In hydroponics, plants grow with their roots in nutrient-rich water, with no soil needed. Aeroponics goes a step further, suspending plants in air and misting their roots with nutrients. These methods are incredibly efficient, using up to 90% less water than traditional agriculture, critical when all water is precious. We'd carefully formulate the nutrient solution, perhaps using treated human waste as organic compounds, creating a truly closed-loop food system. What kind of food would we grow? We'd start with fast-growing crops like lettuce, radishes, and herbs. Later, we could grow substantial crops like potatoes, wheat, and soybeans, rich in calories and protein. Experiments on the International Space Station have already successfully grown plants in space, proving it can be done. The key will be controlling the environment, the light cycles, the temperature, the humidity, and the atmosphere's composition. We might even make lunar regolith itself productive by washing it to remove harmful substances and enriching it with nutrients and microbes from Earth. It would be a long process of soil creation, accelerated terraforming on a small scale. Imagine future lunar farmers tending fields inside vast, transparent domes, looking up at the black sky and brilliant blue Earth. Growing food on the moon isn't just about survival, it's about making the moon a home. The journey to a lunar city is not a fantasy for a distant future. It's happening now. The Artemis missions are laying the groundwork, returning humans to the lunar surface and establishing the Artemis Base Camp, a foothold for long-term exploration. Nations and private companies around the world are designing rovers, habitats, and power systems. We stand at the threshold of a new era of exploration, one defined not by fleeting visits, but by a permanent, sustained presence. The first generation of lunar citizens may already be in our classrooms today, dreaming of walking on another world. What will life in a lunar city look like a century from now? Perhaps it will be a network of interconnected domes and underground warrens, bustling with scientists, engineers, and tourists. Its economy might be driven by mining helium-3 for future fusion reactors, manufacturing unique materials in a vacuum, or serving as a transportation hub. It will be a place of incredible innovation, where the constraints of the environment force breakthroughs in science and technology. It will have its own culture, its own art, and its own unique view of the universe and humanity's place within it. This endeavor is about more than just survival or science. It's about fulfilling a fundamental aspect of the human spirit, the drive to explore, to push boundaries, and to see what lies over the next horizon. We are the descendants of explorers who crossed oceans and continents, who looked up at the stars and wondered. To confine ourselves to one planet forever would be to deny that essential part of our nature. Establishing a city on the moon is the next logical step in that grand, millennia-long journey of discovery. It's an expression of our cosmic curiosity. The first footprints left by Neil Armstrong and Buzz Aldrin were a momentous achievement. But they were just the beginning. The next giant leap will not be a single step, but the collective effort of building a lasting home on another world. It will be a testament to our species' ability to dream, to cooperate, and to overcome immense challenges. When we look up at the moon, we should not see a place of desolation, but a place of promise, a new frontier, a second home, and the dawning of a truly interplanetary future for all humankind. Our ship is ready, the cosmos awaits.